let's continue solving some integrals, or sorry, solving some series using the integral test and p-series. We'll get to p-series eventually, but we're not there yet. So this time, instead of being given the terms, we're given elements of the sequence, and we need to figure out what the general form of a term of the sequence is so that we can apply the integral test. So I've got natural log 10 over 10, natural log 11 over 11, natural log 12 over 12. Okay? Well, what I notice is that these numbers match. But what I also notice is that they don't start at 1. They start at 10, 11, 12. So what I have to do is I have to kind of offset that to make sure that it doesn't... I have to offset that to make sure that it lines up with starting at 1. So if I start this at 1, I get 1 plus 9, 1 plus 9, so that's 10. So A1 is natural log 10 over 10, A2 is natural log 11 over 11, and so on and so forth. So the first thing I want to do is do the nth term test for divergence. So if I were to do that nth term test for divergence, I would get like an infinity over infinity. I could apply L'Hopital's rule. I would end up with 1 over n plus 9 over 1. I would apply the limit again. It would go to 0. So I'm not gonna apply anything there. It's inconclusive. If this was non-zero, we could say it diverges immediately, but we can't. So we got to keep going. Now what I want to do is I say, okay, well I'm going to naively look at that function. Well, one thing I know is that this function is positive because from 1, so starting with natural log 10, natural log is positive for values greater than 1, and then x plus 9 is positive for values greater than negative 9. So this is clearly positive. Now it's continuous because this thing is only discontinuous if we go down to if this thing ends up being 0, which only happens at negative 9, which is also true there. So this thing's positive continuous. Now is it decreasing? You're going to have to take a derivative. Again, if you knew a little bit about the families of functions, it would help you a little bit here, but sometimes with those ratios of functions, things can kind of bump up and down. So let's take a derivative. So we got to do low d high minus high d low for low low. So what I end up with is 1 minus natural log x plus 9 squared. So you have to say to yourself, okay, well this is clearly positive on bottom. So is this going to be negative? Well, natural log of 10 is bigger than 1. It's bigger than 2 even. So it's not going to be close enough to 1. So it's always going to be, this is always going to be bigger than 1. So 1 minus that is always going to be negative, right? If it's 2 or 3 or 100, 1 minus whatever is negative. So this tells me that this is the derivative is less than 0, so it's a decreasing function on the domain of 1 to infinity. So since it's now positive, continuous, and decreasing, we can apply the integral test. So using some u substitution here, we take a u. You'd actually take u to be the natural log here. U is equal to natural log of 1 plus 9. And then du would be 1 over x plus 9 dx. And so you would end up with 1/2 natural log of x plus 9 squared from 1 to infinity. Now when I plug in 1 here, I get natural log of 10 squared. Doesn't matter. That's not that's a finite value. But we really care more about the infinite limit here. So when I take the limit as x goes to infinity, well, natural log of infinity is infinity. infinity squared is infinity. So like nothing about this is not taking us to infinity. So that tells me that this diverges. And so we're going to learn about a test as we go on called the comparison test. And we would have been able to use the comparison test in addition to the ratio test, and we would have been able to solve this divergence a lot more quickly than we did here. But this is a good exercise because the integral test is a really powerful one. So next we have 1 over 10 plus 1 over 12, 1 over 14, 1 over 16. Okay. Well, it looks like it's going up by 2 each time in the denominator. So that's 1 over 2n, because that means it's for every element it's going up by 2. But if n is 1, this is 2, so it looks like my offset is actually 8. So you can verify that out. When n is 1, it's 10. When n is 2, it's 12. When n is 3, it's 14, and so on and so forth. So I feel pretty good about that. Now, hopefully it's readily apparent that the nth term test for divergence will be inconclusive, so we're going to skip it. So I'm going to say f of x 1 over 2x plus 8. Which is 1/2 times 1 over x plus 4. Hopefully you realize this is going to be positive for all x 1 or greater. It's going to be continuous for all x 1 or greater. So is it decreasing? Well, if I look at this, this is just a shift to the left of 1 over x. So if 1 over x looks like this, 1 over x plus 4 looks like that. Just shifted 4 units back. And this is just a scale factor, so it just scrunches it a little bit. But the whole point is, that's clearly a decreasing function. I could take the derivative and do all that stuff, but knowing my parent functions is helpful here. So now I know that it's positive, continuous, and decreasing. So I can apply the integral test. And we keep seeing all these natural logs, so hopefully you feel pretty good about evaluating these limits. This thing's going to be infinity. It's going to diverge. Man, it's like, can we get a convergence series? I mean, we got one last time, but a lot of times the integral test is really useful for showing divergence. It's nice for convergence too, but often we use it to just push something out to show it is divergent.